You scan QR codes every single day on menus, on packaging, bus stops, maybe even on your coffee this morning. And you just point your phone and it works. No big deal, right? But here's a question. What happens if a part of it is missing? What if the QR code is scratched or crumpled? What if there's a brand logo sitting right in the middle, like the Instagram logo, covering a big chunk of the actual code, and it still works? How is that possible? And here's the part that's going to catch you off guard. The technology that makes this possible wasn't even invented for QR codes. It was invented to protect data sent by NASA space probes from space to Earth. Oh, and one more thing. There is a very good chance the reason you are scanning QR codes at all today is because of Toyota. Yeah, the car company. Hi, I'm Kaveh, and today we are going to unravel all of this. The space math, the car factory, and the hidden genius inside those little black squares. To understand why QR codes exist, you have to understand a very specific headache that Toyota had in the early 90s. Toyota runs on a production philosophy called just-in-time manufacturing. The idea is very simple. Every single part only arrives exactly when it's needed on the assembly line. No excess, no waste, just pure Japanese efficiency. But to pull that off, you need to track thousands of components flowing through the factory at any moment. And in the early 90s, they were doing that with regular barcodes. The problem? A barcode can hold about 20 characters, which is barely enough for a short product code, let alone a description in Japanese, which uses kanji characters that barcodes couldn't even support. And on top of that, you had to align a scanner perfectly with the barcode to read it. One of the Toyota's part supplier, which is a company called Denso Wave, got tired of this. Denso assigned one of their engineers, Masahiro Hara, to fix this. His brief was essentially build something better, something that holds more data, scans instantly from any angle, and critically works even when it gets dirty or damaged on a factory floor. 2 years later, in 1994, Hara and his team unveiled the QR code. QR code could hold hundreds of times more data than a barcode. It could scan literally from any direction. And here's the key thing that Hara baked in from day one. It could survive damage because he knew that in a factory, survival wasn't optional and damages could happen to barcodes at any moment. Alright, before we get into the error correction magic, let's take a quick tour inside the QR code, because once you know what each piece does, the whole thing just clicks. A QR code is divided into almost 8 distinct zones, and every single one has a job. These are those 3 big squares in the corners. Their only job is to tell your phone camera that here I am. This is where the QR code is. And this is which way is up and which way is down. And based on the exact locations of those 3 squares, your phone figures out whether the code is correctly oriented or not. No matter if you're holding your phone upside down, sideways, or at any angle. A line of blank white space wraps around each detection mark. This keeps the finder patterns visually isolated from the rest of the code so the scanner doesn't accidentally confuse them with the data. Zone number 3 is a row of alternating black and white squares running between the detection marks. That's a clock signal. It tells the scanner that the exact size of each data module and determines the version of the QR code, basically how much data this particular code can hold. Zone number 4 is the alignment pattern. This smaller square appears in bigger QR codes, and in some versions you don't even see it. Its job is to help the scanner correct for perspective distortion. So if the code is on a curved surface or you're scanning it at a steep angle, the alignment pattern lets the software unwrap the image and read it cleanly. Zone number 5 contains 15 bits of metadata that the scanner reads before it reads anything else. It tells the scanner which error correction level is active and which masking pattern was applied when the code was generated. Think of it as an instruction manual for reading the rest of the code. Zone number 6 is your actual data. This is the actual payload, which could be your URL, your text, your Wi-Fi password, whatever the code is carrying. It's stored in 8-bit chunks. Zone number 7 is error correction data. This looks almost identical to the actual data, and it's also stored in 8-bit chunks, but this is not your original message. This is mathematically generated recovery data, and this is the part that brings the code back to life when it's damaged. But have patience, we are going to dig deep into this just in a second. Zone number 8, which is the remainder bits, is when the total number of bits in the code can't be divided perfectly into groups of 8. So the leftover bits land here, which is a small tidy-up zone to keep the grid clean. Now we are going to be talking about the error correction system and how exactly it works. The error correction system inside QR codes wasn't invented actually for QR codes. It wasn't even invented for anything on Earth, but it was for something in space. In 1960, two mathematicians called Irving Reed and Gustav Solomon published a paper describing a new way to detect and correct errors in transmitted data. And NASA picked it up almost immediately. When you are sending signals from a spacecraft, which is billions of kilometers away, like the Voyager probes, that signal is going to get corrupted by cosmic noise. Reed-Solomon allowed scientists on Earth to receive a damaged signal and mathematically reconstruct what the original message was. The same algorithm that rescued data from the edges of our solar system is quietly running inside your phone every time you scan a QR code on a pizza menu. Now let's forget QR codes for a second and let's talk about points on a graph. Imagine you have 5 pairs of coordinates, 5 x and y points plotted on a graph. Now here's a key idea. If you have enough points, there is one and only one curve that passes through all of them. Not two curves, not a range of possibilities, exactly one. Reed-Solomon takes your data, say the URL youtube.com, and converts it into exactly this kind of curve, a polynomial, a mathematical shape defined by those points. But here's the clever part. Instead of only saving the minimum number of points needed to define that curve, Reed-Solomon generates extra points, more than you strictly need, all of them lying on the same exact curve. These extra points get embedded into the QR code alongside your actual data as what we call redundant code words, which is exactly the same zone 7. Now, when your phone scans a damaged QR code and some of those points are missing or unreadable, it takes the surviving points, runs the Reed-Solomon algorithm, and because there are still some points left, it reconstructs the same unique curve, which is exactly the same one that matches your original data. And from that curves, it fills the missing points, and from the missing points, it recovers your full URL perfectly in milliseconds. But here's the catch. This is important, that if too many points are destroyed, you no longer have enough information to nail down to one unique curve. At that point, multiple polynomials could fit the surviving points, and the algorithm has no way of knowing which one is the original one. Now, the actual math behind all of this runs a bit deeper than what I just described, but honestly, for getting the real idea, what I just walked you through is exactly enough. Not every QR code uses the same amount of redundancy. There are 4 levels and each one is a trade-off. More redundancy means more damage recovery, but the code also needs to be physically bigger to hold all that extra data. Level L is the bare minimum, designed for situations where the code will always be read under perfect conditions. Think of a QR code printed inside a sealed product box. Level M is everyday default. This one you will find on most restaurants' menus and product pages. Good balance between size and resilience. Level Q is a step up for situations where moderate wear is expected, like a QR code on a shipping label that gets handled, folded and scanned multiple times across a delivery chain. Level H means up to 30% of the QR code can be completely obliterated, and the scanner will still reconstruct the full message without breaking a sweat. Which brings us to the logo. When a designer places a logo in the center of a QR code, they are intentionally destroying up to 30% of the data area. So QR codes went from a Toyota factory tool in 1994 to global everyday infrastructure, and the jump happened faster than anyone expected. In 2020, they became the default solution for contactless everything, which are menus, payments, event access, health certificates like vaccines, and none of that would have been reliable without Reed-Solomon. So Toyota needed a better barcode. An engineer named Masahiro Hara built one, and somewhere along the way he borrowed math from NASA that was designed for outer space and made it work on a cup of coffee. If there's a topic you'll always wonder about and want me to dig into it and make a video about it, drop it in the comments. And if there are any questions about QR codes or anything else, my past videos, just leave a comment below and I will check them out and respond to you. And I will see you in the next video. Bye.